This chapter talks about correlation. This correlation examines the relationship between two variables. Think about how often you've used your phone in a classroom environment. Several professors have conducted studies. This one study with the graph on the left looks at college students, how many times they reported that they used their phone during the class lecture, and then the professor correlated it with their test scores. So performance in class is on the y-axis. So the higher you go up, the higher your grade on the test. Smartphone use is on the x-axis. So the closer you are to the right, the greater times you use your smartphone. So when you look at a correlation, basically you plot the data points against each other. For example, the person who used their smartphone the least should be on the left side of the graph. Notice they had a pretty high performance in class. It's pretty high. And then let's look at the right side of the graph. Notice the students that used their phone the most had the lowest grades in class. So this is a correlation. A correlation is a statistical method used to describe the relationship between two variables. A relationship exists when changes in one variable tend to be accompanied by consistent, predictable changes in the other variable. The things that we look at are characteristics of these relationships. We look at the direction. Is it a positive correlation? Is it a negative correlation? We look at the form. In this case, we're going to be talking about linear. And we look at the strength. It can vary from 0 all the way up to 1. Kind of think of it in terms of percent. 0% to 100%. So it goes from 0 to 1, 1 being the strongest correlation there can be. So look at the graph on the left. If you took people in this study were named A through N. Each letter represents a different person. You looked at their family income and their student's grade, and you graphed it. So for example, person A, you would graph the point 31,72. So look on the graph, and that point is the first point you should see on the graph. Then if you plotted all the other points, you would notice that there's kind of a trend. All the dots kind of seem, if you put a line in the middle of them, they seem kind of to form a pattern of going up and to the right. Because the line's going up, the pattern, this would be called a positive correlation. So in a positive relationship, the two variables tend to change in the same direction. So look at the example I have on the left of income and weight. This shows for men. The more they weigh, the higher their income. According to this chart, they looked at, say, a group of men, and they plotted the dots, and then notice the line of best fit. It's the blue dotted line. Most of the lines are pretty close to that blue line, so the correlation may be around 0.8 or so, and it's a positive correlation because they're correlated highly. Lower income means lower weight, higher income means higher weight. Now let's look at the example for income and weight for women. This is a negative relationship. The two variables go in opposite directions. As women's income is higher, their weight is lower. And as women weigh more, their income is lower, and as women weigh less, their income is higher. So this is a negative correlation. I like to think of in terms of Jack and Jill went up the hill. So when you go up, climbing up a hill, it's positive. When you fall down, going down a hill, it's negative. So here's some different relationships you might see in terms of correlations. Look at Part A. This is called a perfect correlation, when all the dots line up and make a perfect line. So the correlation here is negative because the line is falling, and it's perfect, so it's 1.0. You can't get any better than that. Let's look at example B. There's just a bunch of random dots. There's no pattern whatsoever exist, so there is no correlation here. You would say no correlation or correlation of 0. Let's look at C. There is a pretty strong upward trend to these dots. correlation may be 0.8, 0.9. If you put a line of best fit in there, all these dots would be very close to that line. Let's look at part D. This is kind of a weak correlation, but you can definitely see that if you put a line of best fit, it would be falling from left to right. So maybe a correlation of negative 0.4. Let's look at Pearson correlations. This is when we measure the degree and the direction of the linear relationship between the two variables. Again, as we talked about, in a perfect linear relationship, every change in x has a corresponding change in y. And correlations will go all the way down to -1, all the way up to +1. The Pearson correlation measures the direction and the degree or the strength of the relationship. To compute this Pearson correlation, you first compute the variability of x and y separately by computing the sum of scores for the x column of scores and computing the sum of scores for the y column of scores. Finally, you compute the covariability, and this is with a new formula that we're going to be introducing that it's called the sum of products. So basically, the correlation is going to end up being the sum of products over the square root of the sum of squares for x and the sum of squares for y. Why would we use correlation? They're used in a number of situations. Prediction is probably the best one we will be using it for in this class. If two variables are known to be related in some way, it's possible to use one of the variables to make a prediction about the other. For example, ACT scores and GPA from high school and college are pretty well correlated, highly correlated, because ACT scores can predict how well you're going to do in college. They can predict your college GPA. Another way to use correlation is for validity. For example, if a new test measures intelligence, then basically the scores on this new test should be related to scores on other measures of intelligence. We can use correlations for reliability. We can use correlation for theory verification to test to see if there is an actual relationship or correlation between two variables. One thing that is really important for us to understand is that correlation does not mean causation. Correlation describes a relationship only. One variable does not necessarily cause the other variable. Both variables could actually be caused by an outside factor. Actually, establishing causation would require an experiment in which one variable is manipulated and others carefully controlled. We don't have that in correlation. So in correlation, let's look at this example over here. The number of churches is highly correlated with the number of serious crimes. You can see the more churches a city has, the more crimes the city has. However, that doesn't mean that the number of churches, more churches causes more crimes. It doesn't mean that more crimes cause more churches. Instead, you could look at an outside factor, which would be the fact that it would be a large city. In a large city, there's more crimes and there's more churches. Small city, less crimes, less churches. So correlation does not mean causation. Another example of that would be the number of burglaries are highly correlated with the amount of ice cream sold. Well, the outside factor here would be the weather. In the summer, there's more burglaries, there's more ice cream sold because it's warmer outside. In the winter, fewer people are going to get out of their house when there's snow and ice on the ground, so there's fewer burglaries, therefore fewer ice cream sold. So burglaries and ice cream have a high correlation, but that doesn't mean either one caused the other. All right, let's look at interpreting the correlation. Again, a correlation simply describes a relationship, does not explain why they are related, cannot and should not be interpreted as cause and effect. The value of correlation can be affected greatly by the range of scores represented in the data. One or two extreme data points or outliers can have a dramatic effect on a correlation. When judging how good a correlation is, it is tempting to focus on the numerical value of the correlation, such as R equals 0.8. However, a correlation should not be interpreted as a proportion. To accurately describe how one variable predicts the other, you actually must square the correlation. Thus, a correlation of 0.5 means that one variable partially predicts the other, but the predictable portion is r squared equals 0.5 squared, or 0.25, or 25% of the total variability. All right, let's look at correlation and the restricted range. So say, for example, that I gave you the scores only on the right, and you looked at that and you said, oh, no, there's no correlation at all. However, what if I gave you a lot more data points? So now you have the entire graph. Now can you see how with a lot more data points you would be a positive correlation here? So severely restricting the range is not a good idea. You want to have as many scores as you can have. All right, an outlier is an extremely deviant individual in the sample. Look at the graph on the left. There's 5 scores. There's really no pattern at all. However, what if you had just one outlier? So look at the graph on the right. Where's one up there at the top? Well, now you'd be tempted to draw a line through all those, when in actuality, there's really still not a correlation, but it sure looks like there is when there's an outlier, so be careful with that. All right, let's look at the strength of the relationship. Again, a correlation measures the degree of a relationship on a scale from 0 to 1, or you could go from 0 to -1. Remember, correlation is not a proportion. You can look at squared correlations, and when you square it, it's called the coefficient of determination, which is r squared. So let's look at the degrees of these relationships. Shoe size versus IQ. If I took 15, 20 people, plotted the points between their shoe size, their IQ, there is absolutely no relationship at all. That would be no correlation. Relationship between IQ and college GPA. Well, you can see with these points that the relationship is not great, but it is a positive one, rising to the right slightly, so maybe 0.4 or 0.5. And then finally, look at the last graph between annual salary and monthly salary. That's a perfect correlation. So the line would be a perfect line. So that would be a correlation of positive 1.0. It would be perfect. All right. We can do correlation hypothesis testing. Basically, you want to know whether a correlation exists in the population. We will not be doing the hypothesis test part for this class. Let's look at the alternative to the Pearson correlation. Well, we know Pearson correlation has been developed. It's for data that have linear relationships. But another aspect for the Pearson correlation is it must have data from interval or ratio measurement scales. We don't always have that. So other correlations have been developed. These are for data that have nonlinear relationships or data from nominal or ordinal measurement scales. Think in terms of ranked data. So to do a Spearman correlation, you usually use this if both of the variables contain ranks. It measures the consistency of the direction of the relationship. So here's an example. When you have a Spearman correlation, and it's not ratio data or anything, a lot of times you have to rank the scores. So in order to rank the scores to be able to run a Spearman correlation, here's an example of how you would do that. First, you would take all of the raw scores and you would list them in order from smallest to greatest. So look at the scores on the left, they've been listed from smallest to greatest. Next, you would assign a rank. Basically, you would just number the scores, in this case 1 through 7. And then the final rank occurs when 2 or more scores are tied. You're going to calculate the mean of that ranked position. For example, scores, there's 2 3s in the raw scores. Well, they have a ranked position of 1 and 2. So you wouldn't give both of those scores a different ranking. Instead, you would average together the rank of 1 and 2. Well, what's the average of rank 1 and 2? Well, it's 1.5. And the way you find an average is you add up the 2 ranks and you divide it by how many ranks there are. So 1 plus 2 divided by 2 would give you 1.5. So the final ranking for those scores of 3 would be 1.5 each. Now look at the score of 6. There are 3 6s in this category. They hold ranked positions of 4, 5, and 6. Again, we can't have different ranked positions for the same score. So basically, we have to find the average or the mean of the rank of 4, 5, and 6. So you would say 4 plus 5 plus 6 divided by 3. You would get a final rank of 5. 5 is the average. So you would assign all three of those sixes a final rank of 5, 5, and 5. So your final rank column is what you would use for these scores if you were doing one of these examples. All right, the ranks for scores in a Spearman are simply integers. Basically, you're going to rank the X column of scores, you're going to rank the Y column of scores, and you're going to find a difference column. And then you're going to use the equation below to find the Spearman correlation using that D, or the difference, the summation of the D squared column. We'll be doing an example soon.